Hello and welcome to another exercise lecture. In this exercise, we want to calculate the design tornado velocity pressure on a MWFRS type building, which is basically stand for main wind force resisting system. And a building we want to get the tornado velocity pressure on is this hospital right here, which is about 150 by 100 feet. But the area, the hospital is also close to a utility building, which is about 30 feet by 60 feet and is about 10 feet tall. Then there's a water tank right there, and that's 20 feet diameter and 10 foot tall. And the hospital itself is about 5 floor, say 50 feet tall. And when we do and the building is located in Springfield, Missouri. Surface roughness is B, topography not suited on a hill, and the risk category is a 4. Enclosure classification is enclosed. Before we go ahead and start solving this, let's talk about tornado a little bit. So let's just review this go over briefly, and you can pause the video and read these PowerPoint if you want. Tornado speed is just like wind speed, is based on 30 feet above the ground, but it's really based on the effective area of the structure. You want to learn about tornado, go to chapter 32. Let me bring this over here. And this is a chapter 32 of ASCE. They've done a really awesome job talking about tornado. And this is in the United States, this is the area that is really tornado prone region. And then there are all these explanations, what are all these factors are, and we will go over them, and I even give you a flow chart how to calculate the tornado. And this is really useful. Go through all these steps to calculate the design tornado load, which we're going to go through this. And if you know done a wind design, you already been through these things. One of the things I want to show you is, and you look at here, like figure 32.5 is tornado speed for a risk category 3. So each risk category have its own map to calculate the speed. One of the best way I do it, I just go ahead and use the ASCE hazard website and get all that information. And this is again based on a plan of area. This is for 1 foot square, and the area are chopped up in 4 different region, 4 different square footage, which we will calculate in a minute. So this was a 1 foot square, and if you go to the next one, it's a 2,000 feet square, and the next one will be 2,000 feet square. There's one more, I think, 10,000 feet square. And you got to look at your structure, the area you do want to see. Is it going to be 1 foot square, 2,000 feet square, 10,000 feet square, or 40,000 feet square? Then you can use a proper map to calculate your tornado speed. All right, let's go back to the PowerPoint. This is again the effective area. You got to calculate the effective area. Then you got to look at it. Is it a polygon, or is it can I put a triangle around it, or a rectangle around it, and all that stuff. Tornado direct. Then do you have these factors which we talked about in the chapter 32, and it explains all these. You have a factor KDT, and this is how you're going to look at it. Again, I'm not going to talk about it in detail because we're going to go over the example. Then you have a factor KZ, and this is the table we're going to use. Then you have a factor KDT and the velocity pressure, and this is the equation from ASC it's going to be used. And then you have a tornado gust factor, just like the wind is 0.85. Then enclosure classification, just like wind, has to be given. And the tornado internal pressure coefficient GCPI, you can get it from this table. And design tornado pressure from right here, from this equation. And tornado velocity pressure QZT. And then we can use table 32 for a directional factor. And then KVT, we can use it this table right here. 32.141. And the pressure coefficient CP, just like when we have to go to chapter 27, get that. And the source for this example I'm going to do is ASCE 2722, IBC 2024, and a good book, Structural Load Determination 2024. All right, let's get to work. Okay, in order for us to calculate the tornado velocity, we need to find out the effective area. The effective area, when we look at the structure, is a Bogatti structure. We can put a rectangular shape around it. That's one, or we can do octagon. And I think the rectangle is better. And if we go ahead and we can also do it this way too. Say from here, it's going to be kind of diagonally there, and then diagonally there, and then this way. But we're going to use this easiest way, just use the white line effective area, which I just calculated a second ago. It's 150 plus, this was a 30, this was a 60. So now we got 150 plus 30 plus 60 and time 100 gives us 24,000. Remember, there was when we go into ASCE chapter 32, they had the plan area in 1 foot square. I think it was 2,000 foot square, 10,000 and 40,000 and so on. So this will, because our number is 24,000, it's bigger than 10,000. We go up to the next one, which is a 40,000 foot square. Let me show you that right here. We have the map, and there's a lot of these in this chapter 32. So we're going to go to tornado speed risk category 4, that's where we are, and then the plan area 40,000, and Springfield fills around here 103. Or we can go ahead and go to ASCE hazard tool, and that's a good website. Let me bring it up and show it to you. There it is. We can go in here and type in the area, and right here it was a Springfield. So when we type in the location right here, and it's going to be a tornado, risk category is going to be 4, default, that's fine, and we should be able to get the result. And let's get the summary. And right here it says see detail. So let's go to see the detail. And if you click on the detail right here. Remember, when we hit that, it didn't give it to us because there's a detail, and this is really perfect right there. The effective area could be 1, 2,000, 10,000, 40,000, 100,000, 250. Our number was 24,000, so we've fallen right here. And the speed is 103 for tornado speed category 4, and for 3,000 year or 10,000 year is 132, for 100,000 is 183, for 1 million year, and so on and so forth. So we're going to use the 3,000 year right there, and that's going to be basically VT is equal 103. From CE hazard tool also, the basic wind speed is going to be 120 miles an hour. We may need this later on. So now we get down with the step number 1. Step number 2. The exposure category was given, and that was B. So we're good with that. In all direction. And then there was a note right there. So our VT was equal 103 mile per hour, and that should be bigger than 0.5 times V, which is 0.5 times 120, which is 60. So that's checked, and that's based on that's a check mark based on ASCE. That's, if you look it up, is a 32.5.2. Okay, so if you go back to the ASCE, this chart, we did this tornado in a region, we said yes. Is VT bigger than 60 mile an hour? Yes, we just checked that. So now we're going to go to the next one for exposure category B. VT has to be bigger than 0.5. We did that. Now we're going to go ahead and design for tornado is required, and we're going to continue. Okay, step number 2, we're going to calculate the gust factor, and that's from ASCE 32.11. Let's go there, show it to you in a second, and that is right here, 32.11. This is it right there. It says it's equal 0.85. Okay, and let me stop that. We go to the next step, and the next step will be step 3, and that will be calculating KDT. And let's go to ASCE 32.61, the table 6-1, and let's find out what KDT is equal. 32.6. Okay, 32.6 dash 1 is right here. KDT factor. Okay, main wind force resistance system component and clouding, and that is 0.8. So that's going to be 0.8. Let's write that down. KD is equal 0.8. That was that step. Let's move to step number 4. And step 4 will be calculating KZ tornado, and that is given on a table ASCE 32.10-1, and let's go there, see if you can find that. 32.10-1. Oh, right there. Perfect. And take a look at it, see if you can figure it out before I say it. You guessed correct. 1. So we got 0 to 200. Height above the ground. Our height was 50 feet above the ground, so we're going to get 1. And therefore, I'm going to write down 1. And KZ tornado is equal 1. That's a step for A, because we want to calculate the QZT. And let me just go to a different color. So we're doing this to Q. No, that didn't work. We're gonna find here QZT. In order to find that, we need to find KZ, this one first. So we'll go to the step 4B. And in the 4B, we're gonna calculate KE. And that's the ASCE. I think it's, yeah, 32.9, and our KE is equal, let's go to 32.9. So 32.9 right here says ground elevation factor KE shall be calculated using 26.9. Okay, let's go to 26.9. We go to 26.9. It is right here. 26.9 says the ground elevation factor just for their KE shall be determined in accordance with table 26.9. It is permitted for all height elevation KE is equal 1. So KE is going to be equal 1 right there. And let me go back, and we're going to say KE is equal 1. Next, we're going to go to step 4C. And 4C, want to find out the risk category, which is risk category 4 that was given. Let's go to 4D. And 4D is net area, which we calculated, and it's equal 24,000, which we calculated already. And then we're gonna go VT before E, and we just did that. VT was 103 because we need this to calculate QZ. That's why I'm writing all these down. And that was for AE of 40,000 square feet. Let's change color back to green. And then we're going to calculate finally QZT. And that's from ASCE. Let me write it here. ASCE 32.10. And this is for imperial unit, which is equal 0.00256 kz tornado time KE time VT square, which is equal 0.00256 time 1 and 1, and so I'll just double check that time 103 square, and that's equal 27.2 pound per square foot. Now let's go to step number 5. We want to calculate CP factor, and if you remember that we did that for the wind, and let me bring that, that's an ASCE, that was an ASCE 27.3.1, and if we go to ASCE 32.5, it basically refers you back to here. So as long as we go to 27.31. Let me pull that up. So for CP, we have to go to ASCE section 27.3.1 and then get those numbers like we did in my when we calculate the wind load. I have a couple of videos, you can watch those too. So let me go ahead and go over there and show you, and then I will write down the calculation here. And if this is the table we want to get our CP value, it's both for wind load and tornado load. And it's a function of length over the B ratio. Our length B ratio is, depend which way you look at it. If you look at it north-south direction, it will be 100 over 150. If you look at it the other way, it'd be 150 over 100. So for all height from of the building, and for L over B ratio is equal 0.8. And for leeward wall on the other side, it's going to be it all depend your L over B ratio, where is it going to fall. It is going to be minus 0.5 in our case, or minus 0.3, depending which way we're looking at which direction. Then we have to go look at the roof, And a roof is falls into, it's not more than 10%, it's less than 10%. If it's a flat roof, so if the angle is less than 10%, we have to look at the how far in the roof we go from 0 to h over 2, h over 2h, and most likely it's minus 0.9 to 0.18 in all cases. So let's go back to the writing. Okay, and we said leeward was from ASCE 27.3, came out to be forward, no, windward. Windward wall, all height. CP came out to be 0.8. And then we look at the leeward. Leeward wall, we have, well, we got to find L over B ratio. If we're looking at the, let's look at the, let me write this down in a different color. So if you look at the north-south direction, and our L over B ratio would be 100 divided by 150, and that's less than 1. That comes out to be 0.67. So it will be minus 0.5. So CP will become minus 0.5. Then we have sidewall. From the same table, sidewall is all value is minus 0.7. And then we have the roof. And the roof we have to divide it by section. What I mean by divide by one section, it's if I have the roof like this, and this looking at the north-south direction in one of the building anyway, and depend which way the wind is going to blow. If the wind's going to tornado blowing this way, so we're going to have the roof divided in a section. First section is going to be right here, which is going to be from 0 to, code says h over 2. H divided by 2, and h is the height of the building, so it will be 0 to 25 in our case. And that'd be 25, and the second section would be 25 to h, which is 50. And then you can do a third if you want, so we're just going to go 2 of them anyway. Let me go ahead and get on my camera here so you can see me better too. How's that? So now roof, we're going to calculate, it's going to be h over L is 50 over 100, and that will give us a 0.5. And from the same table that I showed you, CP value is equal 0.9 minus 0.9 to minus 0.18. Then we're going to look at the from edge to H, which will be from here to here, and that will be 50 over no, that will be H is 50, so our CP is same thing, 0.9 minus 0.5. I show in a minute, minus 0.5 and minus 0.18, because let me show you the what I was talking about right here. Oops, there we go, right there. So we did 0 to h, this value, and h this value right there. Okay. We can do the same thing for east-west direction. The only thing will be different is for, well, do the same thing. Windward wall. Let me change color. All face is going to be CP is equal 0.8. Leeward, like last time, it's going to be minus point. No, it was oh, it's going to have a different L over B ratio. Wait a minute. L over B is different on the other side. It's going to be 150 over 100, so that's 1.5. If I look at the chart will tell me that's minus point. It's between 0.3 and 0.5. So let me show you right there. So I got to do linear interpolation. Right here, our L over B ratio is between these two numbers right there. Whoop, I can't know it, where my cursor is. So right is between these two numbers right there, because we are right here and we're right there. And if I do linear interpolation, it actually comes out to 0.4. So CP become minus 0.4. CP is equal minus 0.4. Then we have, from there we're going to go sidewall. All sidewall is going to be minus 0.7. And then we're going to go with the roof. It's just like last time. We're going to go from edge of the roof. Our H over L is 50. This time our L is going to be 150. So now we're going to have 0.33. And then from the edge, so the building we're going to look at it this time, if it's like this, we're going to cut it this way because the wind be coming this way. So we got to go this way. And it's CP. We go from edge to 50. So from here to 50 feet. And then we go from 50 to 2H, which would be 100. And so for the first one, when H is equal to 50 to 2H, okay, let me write this down. From H is 50 to edge to, I'm sorry. Let's write it. Edge to 50. Like before, CP is minus 0.9, minus 0.18, those two values. However, from 50, from 50 to 2H, which is 100, and that will be CP is equal minus 0.5 and minus 0.18. And I can show you, these numbers are important. We have to know these things. So it's right there. We're going to be on this right there. Okay, let me close this out here. Okay. Now, we're going to move to step number 6 finally. Now we're done with CP. Step 6. And I'm going to change step 6, find K VT, and that's from ASCE. 32.14-1. So that means we got to calculate KVT for both negative pressure, positive pressure, and wall pressure. Let's go to that chapter, 32.14, right here, 32.14. For a negative pressure, we have 1.1 right there, main one force resistance system. And then for a positive pressure, we have 1 right there. And then for wall pressure, we have right there 1. So we got 1.111. Okay, let me write that down. And we're going to say negative pressure on roof KVT is equal 1.1. Then we have positive pressure on roof and KVT is equal 1. And then wall pressure KVT is equal 1. So that's step number 6. Step 7, we're going to calculate the velocity pressure, and that will be PT. Velocity pressure, let me write that down. From ASCE, that is equation 32.15.1. So let's go take a look at that. And right here, this is the equation. But before we can calculate PT, we already know QI. We did calculate QI. That was QZT. It was 27.2. We did it earlier. So let me write that equation down. Okay. And for roof, we calculated our QI, which is a QH, which is a QZT we had calculated. It was 27.2 pound per square foot. I remember we did it. Let me go double check it so if I make sure I did it. Yeah, right here. That's right there. Okay. So now we have that. And then we're going to calculate for wall. Our QI is equal QZT, which is the same number. That was 27.2. So step 7, we calculating QI. Then we're going to go ahead and calculate. Before I get to this equation, I show you the equation, but there are certain stuff we got to calculate before we get there. So step number 7A or 8, whatever you call it. Step number 8, we're going to calculate tornado internal pressure coefficient. How do you spell tornado? There, tornado internal pressure coefficient. And that's basically CG, GC, PT, PIT, whatever they call it. PIT. We saw that in a formula on 32.15.1. Okay, and then that's from ASCE, from table. 32.13.1, and for enclosed building, which our building is GCPIT equal plus 0.55 and minus 0.18. Let me show you. Let's go to that table. That's 13. It's right in front of me, right here. Okay, so we're gonna go right there. 13.1. This is the table. Other structure, enclosed building and other structure, high 0.55, low 0.18. So that's where those two numbers come from. Okay. So let's go to move on to another step. Let's call it step 9. And then we can calculate basically the PT that I was telling you. Bring it back down here. Calculate the pressure itself based on that equation, which the equation was, I just write it down. PT is equal Q GT K dt Cp minus Qi times G Cp IT. Normally this is when you get to this step you really should go Excel, and then you have everything, because when you do a tornado analysis you got to do a wind analysis side by side based on ASCE load combination. You need to have both of them. Anyway, we're just going to do the step, and you can go ahead and do your Excel. So let's calculate the north-south direction and windward wall. Our PT comes out to be, or not to be, this QI was 27.2 and GT was 0.85, KDT was 0.8, and the other one was 1, CP, no, 0.8. So I'll go 1, 2, 3, 4. 1, 2, 3, 4. Minus 27.2 times plus 0.55 and minus 0.18. So you're going to have two different values here. We're going to have equal. If you calculate that, comes out to be 14.8 minus 15, which is equal 0.2 pound per square foot, and the second value is going to be 14.8 plus 4.9, which is equal 19.7 pound per square foot. Okay, so that was for the wind wall, and we're gonna go ahead and move to the leeward wall. And that is PT is equal 27.2 times 0.85 times 0.8 times 1 times minus 0.5 no, that's right, minus 0.5, and then minus 27.2 times 0.55 plus and minus 0.18. Last time, yeah, that's the same as last time. So we're going to get two value for this. PT is equal. One value is going to come out to be negative 24.3 pound per square foot. The other value it's going to come out to be minus 4.4 pound per square foot. Okay, now we're going to move into, we did leeward, we're going to do sidewall. Change color, so I will not be boring. Topic might be boring, but I don't want to be boring. So sidewall, PT is equal 27.2 times 0.85 times 0.8 times 1 times negative 0.7 minus 27.2 times plus 0.55 and minus 0.18. So our P2 value, it's going to be two different one again. One is going to be minus 28 pound per foot square, and the other one is going to be minus 8.1 pound per square foot. Now we gotta go to the roof, and that's gonna be a little bit tight. Roof, let me change color. We go pink. Pink is good. So we're gonna go from where the wind blow, windward, edge of the roof to 50 feet. Okay, and PT is equal 27.2 0.8 times 0.85 times 0.8 times 1. No, was 1.1. I take it back. 1.1, and then time minus 0.9. Then this whole thing minus 27.2 time plus 0.55 comma minus 0.18. Now we're going to get two different value again. PT is equal minus 33.3 pound per square foot, and PT is equal, the second value, the negative 13.4 pound per square foot. And then we're going to go from 50 to 2H, which would be 100. PT is equal 27.2 time 0.85, 0.8, 1.1, and then time negative 0.5, and minus 27.2 time plus 0.55 and minus 0.18. So our answer comes out to be PT1 gonna come out to be minus 25.2, and the other PT is gonna come out to minus 5.3. Okay, so now we're gonna go ahead and show those calculations we did in a north-south direction, and look at the east elevation. So the height of the building is 50 right here. So we have the positive internal pressure, those, and these will be the number, the diagram. And for the other side, south elevation, for positive internal pressure, we put those numbers in, and that's how the diagram look like. Again, this is a north-south direction. And continue with that, we're going to go to negative internal pressure. In the east elevation, we have these numbers, which we calculated. Then in a south elevation, this will be the numbers. Again, this is for now north-south direction. You can do your own east-west direction, see how you come up with. Okay, next we're going to go ahead and calculate the go look at the different cases. Let me bring out the PowerPoint here for a second. We have ASCE 27.3.8. The building must be designed for the design load cases. So let's go, and there are 4 different cases. Let's go to the ASCE, and that would be, I think it's right here. There we go. If you go to 27.3.8, it says you gotta evaluate all these 4 different cases. Case 1, full design pressure on a project wall area. Case 2, and case 3, and case 4, and then they will give you the moment for the torsion and what we have to do. So take a look at this page, pretty good. I'm going to go back to my PowerPoint. And so this is a case 1, the full design tornado pressure act on a projected area perpendicular to each principal axis. And then we're going to look at the case which was a 75% of the design tornado pressure on the windward and the leeward wall are applied to the projected area perpendicular to each floor. And here the thing of it is, building along with the torsion moment, roof pressure are equal to 75% of those in case 1. The tornado pressure and the torsion moment are applied separately for each principal axis. Then case 3 is the 75% of the tornado pressure of case 1. And so is case 4, 75% of tornado pressure and torsional moment in case 2 act simultaneously on a building. So let's go ahead and work on case 2. Let me close this out here. We're still staying with the north-south direction here. Don't have a time to do the other direction. And I said that was 75% of PWY, and that's the equation from that page I just showed you on ASCE, which is equal to 0.75 time, in this case, let's use this one, 19.7, which is a 14.8 pound per square foot. And then we had the same thing, 0.75 time P, and the other side. These are basically, let me go back to here. Right there, and make this bigger so you can see it. This is what we're doing in case 2. We have PWX and PWY, windward wall design pressure acting on X and Y principal axis. we have PLX and PLY leeward wall design pressure acting on X and Y, and we have EX, EY essentially from X, Y direction. And that's where they are. Let me go back to the writing so you know where they come from. That's the reference right there. So 0.7 for the leeward wall is 0.75 times 4.4, and that is equal 3.3 pound per square foot. And then our EY is plus or minus 0.15 times BY, check the page out, which is equal plus or minus 0.15 times BY was 150 and BX was 100 feet in the direction. So this is equal plus or minus 22.5 feet. We need that for torsion calculation. So MZ is equal 0.75 times PW Y plus PW the LY, sorry, and BY EY is equal, that was 14.8 times, no, take it back, got a plus or minus there. So the 0.75 already been multiplied, we have calculated right here, and that's going to be a 14.8 plus 3.3 right there, and multiply BY, what's the 150 feet, okay, 150 feet time, let me do this over here, MZ is equal 14.8 plus 3.3 times 150 times plus or minus 22.5 times 5 unit of height divided by 1000, and that's going to be plus or minus 305.4 foot cube. Let me explain where this come from, this 5. If we go into the the code itself, it says MZ is a torsional moment per unit height acting on a vertical axis. So we're going to go every 5 unit height is at 5 feet, and that's where it come from. Let me go back to my documentation here, and so that was case 2, and the rest of them is basically case 3 is at 75% and case 4 was 75%. So next we're going to look at the diagram, how we're going to apply to the diagram. Alright, so the diagram for that would be right here for case 1, and for case 2 it will be this, we have the torque in it, torsion, and for case 3 and 4 will be down and bottom here. This will conclude this lecture, and of course the one thing you have to remember is kind of important. Put this in Excel, and when you do that, you have to do a comparison of the design tornado and wind pressure for a windward and a leeward wall over the height of the building. And for negative internal pressure in the north-south direction, also positive direction, you compare both of them. And again, the ASCE load combination requires these things. I hope you liked it. Please subscribe or give a thumbs up. Thank you.